Now the how is the tricky part. So the how are the physics equations described using math symbols. So let's look at them in order and explain what they are. And then we will focus on the last two equations. So the first equation, equation 1, is called Gauss's law. And it looks like hieroglyphics because there's some funny symbols with triangles and dots. So for those of you who've taken the course, you'll recognize del, the upside down del with the dot, and that is the divergence, which measures the expansion of field lines. So if you can imagine field lines emanating from a charge, the field lines are expanding out, like what I call a radial porcupine. So that's equation 1. It's called Gauss's law for electric fields. The second one is Gauss's law for magnetic fields. So you'll notice that the right-hand side of equation 2 is 0. Divergence, that operation in front of the letter, is basically an expansion or contraction operation in terms of the field lines. Well, for the electric case, you do have expansion and contraction if you imagine the field lines going radially out from a point charge, but not for the magnetic case. And what equation 2 says is that we have no magnetic charges. Equation 3 is the one without which we wouldn't have any lights. It's the generator equation. It's Faraday's equation. It says that a rotating electric field induces magnetic field. So that's the principle on which the generator works, and we know that as Faraday's law. Equation 4 looks very complicated. It's got 3 terms on the right-hand side, and it's got this del, the triangle with the x. That's called the curl operation. So what that says is that the rotation, it looks at the rotation, in this case the field H, and that rotation has an axis. And we know that if you have a magnetic field, it's circulating around a current. And those 3 terms on the right side are the different types of currents. The first one is called the displacement current. It's actually a current density to make the units match on both sides of the equation. The second one is Ohm's law current. J is equal to sigma E. That's like in Ohm's law, I equals V over R. And the third one is a battery or a generator, an external source. Now, one of the issues in the course ELEC311 is the solution of these equations for the different wave objects. And we pick wave objects for which the solutions are fairly straightforward. So now I would like to simplify these equations, and let's see if we can get a little bit of intuition around the wave objects. So basically in the next slide you'll see all the right-hand sides are 0. Let's just look a little bit at equations 7 and 8. So in equation 7 you can see that you have this operation of the curl, and it's acting on E. So find the rotation of E, and that'll give you the axis of rotation, which involves the time-changing magnetic field H. So you can think of this right side as like an axis, just like my pen is, and the E is circling around it. The second equation is very much the same. It's now we're looking at the curl, the circulation of H. Okay, so now we have an H circling around, and then the time-varying E is along the axis of rotation of H. So those 2 equations, 7 and 8, are coupled. And to illustrate the coupling, after I erase this, we're going to actually show it in 3D with some help from Andrew and Michael. So Andrew, could you switch the slide off? And the two of you come up here and we'll construct our circulating E's and H's. So Michael, you sit over here, and this is the circulating E. Andrew, and I'm going to do the H that comes, so H is going here, but it's circulating, and then through the H, there's another circulating E. So you can see a chain link here. And this chain link is supported and actually spreads out in two directions, and that's how the waves are generated. Thank you, gentlemen. Now, Andrew, could you bring up the slide again? And we're just about done here. I just have a comment to make. So we have these two coupled equations, this one and this one, and we apply the operation of this to each of these equations. We take the curl of 7 and the curl of, and then expand it, and then use the other equations to actually get a wave equation. And I won't do that in this test case, because that would take us another 20 minutes, and again would look like hieroglyphics. But the point is that, and the interest of this is equations 7 and 8 combined give us the whole wave-like behavior of electromagnetic waves for all the wave objects that I presented earlier. I hope that serves as a good introduction to course design and its application in ELEC311, along with some of the material and a little bit of fun with the picture. Thanks for watching.